Okay, so here's the fourth and final lecture on the topic of surface integrals. And what we've done so far is we've been discussing different types of surface integrals. So here's one type that we can discuss. So basically, we have some sort of surface which is given by the yellow surface over here in R3. And then we have a surface element over here. The vector surface element, ds, with a vector sign underneath it. Well, what is it? Well, it's something which has the same magnitude as the scalar surface element. This is just going to be the surface area of that tiny element. But along with that, you attach to this unit vector which points in the normal direction. So this is actually in R3, so it could be pointing in that direction, or it could be pointing in the opposite direction. So this is only defined up to a plus or minus sign, but when we're doing an integral, we have to make sure that the normal vector is consistent along the surface. So if it's pointing out in this direction, then we continue to have it pointing in that direction as we proceed. Okay, so given these situations, there are two types of integrals that we can talk about. So one of them is a flux integral where you have a vector field f, and by taking the dot product with this, you're looking at the amount of f which is going through, which is passing through the surface, because you're projecting f in the normal direction, and then you're adding that together. This is called a flux integral, where f is a vector field. Or you can have f being a scalar field, little f being a scalar field, and in this case, you can have just the area ds as being the sort of the scalar version of the surface element, where this just incorporates a magnitude and no direction, and then you're doing an integral of this form. So last time in the third lecture we looked at this, and what I want to do is I want to do another example related to the flux integral, and this example is going to be used using spherical polar coordinates. So let me just remind you of our definition of spherical polar coordinates in this course, and this was done in the second lecture as well. Of this section. So given a point in R3, so rho is the distance to the origin, phi is the angle which is measured downwards from the positive z-axis, and then if you drop down a perpendicular into the xy plane, and then draw this line from the origin to the point at which the perpendicular comes down, theta is the angle measured from the positive x-axis in the anticlockwise direction. So it's a standard polar coordinate theta. And then we have certain conditions on this, and then we can write down x, y, and z in terms of these coordinates, right? So z is rho cosine phi, because you take this rho and you project it in that direction, and then rho sine phi is the projection. It's the length of that vector, and then you do have a cosine, and then you have the sine in order to get the xy coordinates. Okay, just a reminder about that. Now I want to just mention a few other things related to the coordinate system like this. So in our rho phi theta coordinate system, we also have unit vectors. So the unit vectors correspond to what happens when you increase each of the coordinates by a small amount. So if you look at rho, if you increase rho by a small amount, so here was our original point, you get further away, right? So rho is on this line, this straight line that you draw to the origin, so you get further away. So the direction in which you proceed is the direction of the unit vector E rho. I'm going to call this E rho. So that's going to be in that direction. And we think of this as a unit vector. We have to have this as a unit vector. So similarly, you can think of what happens when you increment the other coordinates, right? So phi is measured downwards. So if you're at this point over here, and you increment pi, you increase phi, you sort of go downwards. So the direction in which you're going is the direction of the unit vector E phi. And similarly, if you increase theta, so theta is this angle here, so that means that you're moving more in that direction. So in that direction is in that direction over here. So that's e theta, the unit vector e theta, and all of these unit vectors are at right angles to each other because of the way that things are set up. So these angles are at right angles. So it's an orthogonal coordinate system, and that's something that we're going to be using. Right. Okay. Now, the reason I went through this is because I want to do a sort of a more applied problem related to a flux integral, and this is related to an electric field. So the electric field due to a point charge which has charge q, which is usually would be in coulombs or something, which is positioned at the origin, is given by this expression over here. Right. So so what this is saying here is that so the electric field is a vector. Okay, and if you look at the right hand side, this is a vector which is pointing in the direction of E rho. So that's a unit vector in that direction, but the size of this is given by this quantity over here. So Q is the charge, epsilon naught is a physical constant. We don't really need to worry about it too much. I think it's the permittivity, I believe, vacuum, but rho here is the distance to the origin, right? So this is rho squared. So this is just an inverse square law, basically, right? The electric field, the size of the electric field goes like 1 over the distance squared when you have a point charge at the origin. So what are you asked to do here? You're asked to find the electric flux exiting the sphere rho equals A. Exiting means going out, of course, across the sphere. Rho is equal to A, right? So rho is the distance to the origin. So this is a set of points which have a distance A to the origin of the sphere of radius A. Okay, so looking at what's going on here, so I have my XYZ coordinates like this. So here's my S. My S is a sphere of radius A. So I would have on this sphere, I would have a little area element. At each location is going to be slightly different, but I have to ensure, of course, that this is pointing outwards. Well, what about E? E is a vector field, and it takes on different values depending on where you are. And what we're really interested in is just E on the surface of the sphere. So on the surface of the sphere, it's of course pointing outwards in that case. So at different points, it's different. But what we want to do is we want to calculate the flux of E exiting the surface. So that flux is given by this expression over here. So at each location, you look at the projection of E in the direction of the outward pointing normal. And you essentially add them together, right? That's what this is telling me. I have to do this. So here's my definition of the flux of a vector field. In this case, this has a physical meaning. This gives you the electrostatic flux exiting, going outwards, because my ds is pointing outwards in this direction. In this case, just a little item of notation. Now, I'm going to put a little circle around this double integral sign, and that circle indicates that it's a closed surface. Right, it's a closed surface. Why is this surface closed? Well, the surface is the sphere. So once I have the surface, there's the inside of the sphere, and then there's the outside of the sphere. So it's actually going to be a closed surface. So you might remember that we also talked about having closed curves when we were talking about line integrals. And in that case, we put a circle around it as well. So putting a circle around the integral signs means that this is specifically a closed entity. So in this case, it's a closed surface. There's an inside and there's an outside. So the flux in this case is that, right? So that's just sort of notation. Okay, so how do we need to do this, right? So we need to calculate this, and we need to calculate this. Now you might remember that this ds is sort of the complicated beast. So we need to figure out what this ds is in appropriate coordinates. Now we've actually done this in when we calculated the surface area of a sphere a couple of lectures ago. We had to come up with the parameterization of our surface. So the parameterization of the sphere, we can use these coordinates here. So rho is just always equal to a constant, but phi and theta take on all the values that they need to take on. So this thing corresponds to essentially a latitude, and this is corresponding to a longitude on the skin of the sphere. Okay, which means that a general point R on the sphere is now parameterized only by these two things, phi and theta, because A is constant on the sphere. And then the x coordinate is going to be A sine phi cosine theta. So we had a rho over there earlier. That rho is equal to A. That's your y coordinate, and that's your z coordinate. So here's our parameterization. And why do we do this parameterization? Because that helps us figure out what this vector surface element is. And how do we figure this out? Well, we have to take the cross product between these two partial derivatives. These are the two parameters, and then we have the differential elements corresponding to the two parameters, right? So that's what we have. Okay, we've previously done this. So what I need to do to calculate this is I need to take the phi derivative of that. Then to calculate this, I need to take the theta derivative of that, and then I need to take the cross product of these things. So it's a straightforward calculation, and we've done this again 2 lectures ago when we were looking at that example, looking at the surface area of a sphere, and then we got this thing here, right? So this is what we got in that case. So I'm just going to quote that. Now, if this is the sphere, so the yellow thing is the sphere, and I have a point on the sphere. If I pick a particular point, there are these constant phi curves which are on the sphere. These are constant latitudes. There's also constant theta curves going along the sphere. These are constant longitudes, right? So so E theta would be the direction in which I would go if I'm increasing theta slightly. Right, so if I'm increasing theta, I'm remaining at constant latitude, but I'm going in the direction of increasing longitude. So what I would get is a vector which is tangential to the curve over here, because this is the curve in which phi is equal to a constant. And when you're taking a partial derivative, uh, that corresponds to keeping all the other variables constant, right? So that corresponds to E theta, and in fact this is indeed the direction of this quantity over here, because what is this? So this is just taking the partial derivative of your position vector with respect to theta, implying that you're keeping phi constant in that case, right? So E theta is a unit vector which is points in the direction of R theta. So of this partial derivative. Similarly, E phi is going to be a unit vector which is in the direction of the partial derivative of R with respect to phi, the direction of increasing phi essentially. And what that's going to be is that because you keep theta constant, that's going to be tangential to this thing over here, which would be a constant longitude. Yeah, constant theta. Anyway, so we got these two vectors like this. So what's pretty nice is that the vector E rho, which is the third unit vector, it actually points outwards from the sphere, right? So it's a bit difficult to draw this the way that I've drawn it, but it's sticking outwards from the sphere, directly outwards from the sphere. And we do know that this is an orthogonal coordinate system. So these three vectors are all mutually orthogonal to one another. They also have length 1. Okay, and something which is pretty nice is that so just like I, j, and k have these properties, let I cross j is equal to k and j cross k is equal to I, and so on. So just like that, well, these vectors have those properties as well. So E rho I can find by taking E phi and crossing that with E theta, and you can kind of see that if you think of applying the right hand rule to these two vectors. You take your right hand rule, put the fingers in this direction, curl the fingers towards that, your thumb is going to be pointing directly upwards from the sphere. So there's an ordering here. If I take E theta cross E phi instead, this cross that instead, I'm going to get negative E phi in that case, right? So which is why when we have these coordinates, we do think of them, we have to write them in the correct order. So it's rho phi theta. Right, to be a right-handed coordinate system. So that's something that we use. Okay, so we have this property here. Now it turns out that this thing here is actually equal to E rho, and you can figure that out if you think about it a bit, because you've got your origin out here, and your origin out here, and this vector from the origin, which is the center of the Earth, if you will, to this point on the surface of the Earth. It's just a continuation of that, right? It's a continuation of that straight line. You're pointing directly outwards. That's what gives you the direction of that. But this point over here has position vector, which is given by a sine phi cosine theta, a sine phi sine theta, and a cos phi. In fact, we've written that somewhere over here earlier on. Here we are, right? So that's exactly that. That's your position vector at the general point. So clearly this vector, right, is if I put an a here, and an a here, so this vector is pointing in the correct direction. So what do I need to make sure that this is a E rho? Well, I have to ensure that this is a unit vector. Is it a unit vector? Well, if I take that squared plus that squared plus that squared and add them up, I leave this as an exercise, you'll find that you actually do get 1. So this means that this is E rho. Okay, so R phi cross R theta is therefore equal to this stuff times E rho. Right, so that's pretty nice. So that's what I've written down over here. Okay, now what was my whole purpose of doing this? Well, what I wanted to do was I wanted to figure out what ds was. So ds had this formula over here, and then so if I just put in what I figured out now here, so I get a squared sine phi E rho times d phi d theta. Right, so that's my ds. The vector surface element ds is given by that quantity over there, and I'm not scared by the fact that there's a vector over here, because, well, this side has to be a vector. And so this does have to be a vector. It's got differential elements which are related to the two parameters that I have over here as well. Now, what else do I know? Well, I needed E, right? What I want to do is I want to calculate E dot ds. So what is my E? So this is given to me in the problem statement. My E at a general location rho phi, this is a mistake. That should be a theta. Rho phi theta at a general location is given by this expression over here, and we have, of course, the inverse square law, right? So Q is a constant. That's just the charge on that of a point charge. So all of this stuff is a constant. So the important thing is that it's 1 over rho squared, and pointing in the direction of E rho. Okay, but I'm going to actually need to calculate this. What I'm trying to calculate is this thing over here, right? I'm trying to calculate E dot ds on the surface of the sphere. right? S. I need to calculate this. So when I'm doing this, you can see that this stuff therefore needs to be evaluated on S, on the surface of the sphere, which then tells me that what I really want to do is I need to figure out what this is on the surface of the sphere. And what do I know about this on the surface of the sphere? Well, the sphere is given by rho is equal to A. So what I can do is I can just simply erase out this rho squared, and I'm going to put in an A squared because rho is equal to A. So everything out front here is actually going to be a constant. So the magnitude is going to be the same. It's just the direction which is changing as you're going to different locations. Okay, so now we are in a position to just go ahead and do the calculation. So I've done lots of preliminaries here, but the rest of it is going to be very, very quick and very easy. So here's my E, which I'm going to stick in there. And here's my ds, which I'm going to stick in there. So I just need to take the dot product between these two things. And that's what I've written up over here, right? So here is the E that we had. And here is my ds. So I've just taken the dot product. What else do I need to do? I need to make sure that I write down the limits appropriately. So theta is over here. So these have to be my theta limits. Theta is the azimuthal angle, is the one which goes all the way around to give the longitude. So I have to go from 0 to 2 pi in that case. And then I need to have my oh, that's again a mistake. So this is d phi. So then I need to have my d phi. Phi goes from the north pole to the south pole essentially. So I have to have this going from 0 to pi. Okay, so this is the integral that I need to do. Right. So what's going to happen is some pretty nice things are going to happen. In the first place, I'm going to pull out everything which is equal to a constant here. So all of these are constants. Yeah. That's a constant, but I'm going to be multiplying this by a squared as well. And you can see, lo and behold, the a squares are going to cancel. And if I pull out the remaining stuff, I have q over 4 pi epsilon naught is what I have remaining. And now that means I've dealt with that term. I've dealt with that term. Okay, what do I have remaining? So I have this vector e rho dotted with, well, that's an E rho. E rho dotted with E rho is just one because these are unit vectors, right? So that vector, unit vector dotted with itself is just one. So that's going to give me one. So in effect, I can actually just ignore anything to do with that, ignore anything to do with that, and ignore this dot as well because I've actually taken the dot product. What's remaining is just a sine phi. So I just have the sine phi. So I have 0 to 2 pi, 0 to pi, sine phi, d phi, d theta. Okay, and when I'm doing this integral, of course, I can just think of the fact that, look, that thing is going to be a constant with respect to the theta integral, right? Because it only has a phi in it, and there's no thetas over here as well. So that's just going to be a constant. So I can pull it all the way out of the theta integral. So I'm left with just two different integrals. Then I have this, and when I pull this out, I have 0 to pi of sine phi d phi. And then what do I have remaining? I have 0 to 2 pi of d theta. Okay, can we do these integrals? Of course we can. This is kind of trivial now. So I have that constant out front. So over here, I write cosine phi with a negative sign. And I have to go from 0 to pi. And this other integral is just completely trivial. That's just going to be 2 pi. Because it's the integral of the function 1. And when I do this integral, what I'm going to get, well, cosine of phi is -1 and cosine of 0 is 1. So this gives me a factor of 2, as it turns out. So that gives me a factor of 2. So this pi and this pi will cancel. This 2 and this factor of 2 will cancel with this 4. So you're left with this q over epsilon naught, right? Which is pretty interesting over here because, so from the physical perspective, you just had a point charge at the origin, and we were trying to figure out what is the electric flux which exits a surface which is a sphere of radius a. The answer that you got is independent of a. So it doesn't really matter how large your sphere is, you're always going to get the same answer, which is kind of interesting as well. So this statement over here, the fact that that is equal to that, is actually a special case of one of the Maxwell's equations, or if you prefer, Gauss's law of electrostatics, which is telling you that the electric flux exiting a surface is actually 1 over epsilon naught times the charge contained inside it. Right. So if you go on to study electromagnetics, you'll look at this in more detail. Anyway, so here's an example of a calculation of a flux integral, where in this case we took advantage of a certain spherical symmetry, and therefore we use spherical polar coordinates in order to do this calculation. Okay, so what have we talked about over here, right? So in this multivariable integral, multivariable calculus segment, we talked about a whole bunch of different integrals. So what I want to do is I just want to quickly summarize those at the end of this lecture. So one of them was this concept of multiple integrals. So you could get double integrals of this form or triple integrals of this form. And in this case, we would call dA to be the area element and dV to be the volume element, and you would have some sort of scalar valued function that you're integrating over some domain. In this case, your domain it would be in R2. In this case, your domain would be some object, some part of R3. So we talked about those multiple integrals. Then we talked about line integrals. Also we can think of them as path integrals. And the two common ones are these two over here. So this one is when you have a scalar field f and you are integrating it with respect to d little s here. So that's a little s, which and that's the arc length element. And the arc length element, well, it's going to be actually the length of the line element. Right. So, well, let's look at line element first. So the line element dr is this vector over here, where you are incrementing each of the coordinates by differential amounts, dx, dy, and dz. It's that thing over there. And then, of course, the length of that is going to be this squared plus that squared plus that squared, square root of, and that's what this is. That gives us the arc length element. So here's an integration, a path integral with respect to arc length. Here's another type of path integral, and in this case we motivated this by using the concept of work. So if I have a vector field, I look at the projection of the vector field in the direction of motion, and I integrate this along a curve C. That's going to give me an integral of this form. Okay, and now finally, what we've talked about in this bit of lectures is surface integrals, right? So surface integrals are integrals of the form f little f ds or capital F dot ds. So in this case, I have a scalar field f, and my ds, there's no vector symbol here. My ds is just a scalar area element, a scalar element on my surface, on my two-dimensional surface S. And in this case, what we have is in the second case, what we have is a flux integral, right? So and then this is our relationship. Okay, so that's the end of this lecture.